Hi, I'm Jason Catron with Vivet Technology. The manufacturing world has been dominated by Henry Ford's innovative and transformative linear assembly for well over a century. But as a nation, we're really far behind other countries in terms of EV battery production. That's about to change. Today I sit down with the Director of R&D from Vivet Technology, MJ, to discuss a revolutionary new assembly process that's going to take the world by storm. MJ, who is Vivet Technology?
So Vivet Technology is an R&D company. It's a manufacturing technologies R&D company. And we built it to introduce technologies that make step changes in the industry. The reason we do that is across this past century, all the technologies that were developed were accumulated to develop equipment. We think there are different ways of developing new technologies that will introduce step changes. That is a huge difference. Just like when Henry Ford introduced the assembly line, it was a huge change from the era before that. Now we're trying to think of ways or methods to do that kind of change to manufacturing.
Interesting.
Now the special thing about Vivet is our team is coming from different industries and different fields. So we have people from computer engineering, we have people from manufacturing engineering, we have people from different industries like food, pharmaceutical, automotive. They're coming with different perspective of manufacturing. And this is where we come into the game, looking at all these minds, all these possibilities, putting them all together and trying to figuring out what is the next step change in the industry that we can make. And one of our biggest projects right now, it's our flagship today, is what we call the RLP, and this will be a big change. The repeating layer process is a very interesting mathematical approach to manufacturing. So basically what we're doing here is we're offering an alternative theory or alternative method to design manufacturing system or assembly systems than the traditional method that is the assembly line.
So the assembly line started everything, right? It started the Industrial Revolution, it helped us win World War II, and I mean, it's the mainstay, it's a standard in manufacturing. So, I mean, really can RLP do that we haven't been doing already?
Assembly line is used to build everything from the bag of chips to the rocket ships. Now, that means it's a very general case that fits everything. And with that comes the idea that if it's a general case, it's not optimized for anything. It's a general case for everything.
Okay.
Now, this is where you obviously lose optimization or utilization. And this is where the RLP comes in. The RLP is optimized for a specific structure of product. And it happens that product structure fits like a little over 70% of all manufactured products across all industries. We're using that structure without even knowing it's a special structure that the assembly line theory is not optimized for it. And this is why we build the RLP. The RLP is optimized for that specific structure. And with that optimization comes high levels of modularity, high levels of time utilization, and resource utilization.
There's got to be a lot of benefits to what you're talking about. I've already seen a couple of those here, but can you tell me some more of the benefits? Like, what about the efficiency?
One of the main numbers we look at is the what we call OEE, the overall equipment efficiency. And that number our goal when we make any assembly line is 85%.
That's it?
That's all we can do.
Okay.
Okay, that is our goal. Now, in the RLP, that number starts at 92%.
Oh.
This is built in the process. We're not using special equipment. This is built in the math. The utilization of time and resources is very high in the RLP, where that number goes up to 92%. Now, this is in the initial level of the system. As the system scales up, which we're going to talk about it later, as we scale up the system, that failure, that 8% will go down. So we will eventually get to a 99% efficiency or overall equipment efficiency because the system stays up no matter what happens.
Okay, so then talk about maintenance.
So in maintenance, you have to take the system down. You have to take some of the machines down. Regardless, as we said, no matter what happens, the system stays up. So what's going to happen is you bring one of the machines down, the system keeps running. The system will automatically bypasses that machine. And because we're running a system controller, so when you go to that machine, you're trying to run a maintenance on it, you go bypass the machine and the system adjusts itself and the system keeps running production on a little lower capacity, but we're still in production. We never stop it.
So you can remove a machine from the entire process and,
whole thing.
Then the whole thing keeps moving.
Yes.
That's incredible. Okay. That also sounds like a problem for a bottleneck situation, which I know the assembly line can have bottlenecks. So how does that attribute to the RLP?
So since we changed the underlying math behind everything, the design of the system changed. The shape of the system changed. The flow of material changed. So bottleneck is no longer part of the issues for that manufacturing methodology.
Is there any machine dependency?
Here's the idea. Because the system is not built depending on every single machine, but it's built to depend on layers.
Okay.
So more layers you have in machines, less dependent you are on machines. So basically, as we said in maintenance, you can take a machine out or a machine can fail and the system is still running capacity on a lower capacity, but it's still running. You're not changing machine speeds. You're not changing part speeds. Everything is still functioning exactly the same way, but if that machine out, you lost a little capacity, but you're still running. Never stops.
Never stops. Okay. All right. So since we're talking about the manufacturing world,
yes.
Tell me about the throughput.
So since the system is, as we said, scalable, you can start with a very low throughput with your system. That's what we call a basic level of system. And as you scale that same exact system, we're not adding new systems. We're scaling that same exact system, you're going to increase your throughput.
You've talked a lot about the benefits on the manufacturing side, but as we know, there's always two sides of that coin.
Yes.
Tell me more about the investor side of that.
So basically, when we go 100% increase in production, we only need to increase the number of machines or increase the number of investment, the amount of investment by a part of that number.
Wait, now hold on a minute. I know when you get a system that's running, right, and you want to double capacity, you've got to build a whole new system. That's going to take more real estate, that's going to take more footprint, so yes. How is this possible?
Traditionally, that's true because we're dependent on every machine to make that production, and the system is balanced. With this kind of system, no. You only have to add the repeating layer. For example, in this case right here, this is a prototype of a sample of a system for battery manufacturing. And what we're doing here is basically we're saying a layer is 2 machines. And every time we add 2 more machines, we're doubling the capacity. So if you start with 100% capacity to go 200% capacity, you only need 150% investment. You're not doubling your investment anymore.
How is that affecting the footprint?
Same calculations. If you're doubling your production for, like in this example, 50% of the system, okay, you're only adding 50% of the system size. So your real estate or footprint increases 50% only instead of 100% for the 100% increase in capacity. And this is a huge advantage that we never seen in the traditional manufacturing, where if you want to scale your system, you add the whole thing. You have to build the whole system all again.
Right. Interesting. Okay, so you can produce more with less footprint.
Yes.
That's pretty incredible.
Yes.
It sounds kind of revolutionary. I think we've used that word before here.
It's a huge and never existing in the current methods of designing assembly systems.
Like how fast can people start making money out of this machine? Okay.
With this system, what do you have today? 100,000? You build a system that does 100,000, and that system will be much smaller. So now you're in the market, you're producing, and your product is in the market much faster.
How much faster?
About 50%.
50% faster.
About 50% of
You can
that
start
time.
smaller, you can work your way up.
And then when you work your way up, you can scale it much faster than the traditional method, because in the traditional method, you have to build a whole system. In this method, you're basically building a half a system. So it's not only half. It's much, much faster than what we can think about in the traditional method. Not even comparable.
Even comparable. Well, this sounds really fascinating, and I want to know one more thing.
Yes.
How does it work?
Now, have we done the studies and the simulations and the calculations of how? Yes, we have. We've seen the numbers. We've seen the difference between those numbers that the RLP can generate and the numbers that we can traditionally do, and the difference between the advantages of both systems. But today we're going to explain what's happening in this prototype and how it works for the battery industry.
Fantastic. Let's have a look. I'm here again with MJ, and we're standing behind a prototype of the RLP. Show me what you got.
Okay, so the main thing is, as we said, we're going to start from the product, and what we have here is some 3D printed figures that represent a battery module.
Okay.
And that battery module, for the process we have right here, have 8 cells. So regardless the type of cell, keep it in mind, we're looking at the structure of the product and how it's built. We don't care what type of cell. What is the geometry of the product itself, we don't care about that. So this battery module can be cylindrical, can have cylindrical battery cells, or pouch battery cells, or even prismatic battery cells. It doesn't matter.
Okay.
It can have multiple different design structures. It doesn't matter, as long as it fits the criteria. And the main criteria is it needs to have several layers of the same set of products or parts.
So like cell negative, cell positive, cell negative,
yeah,
or
exactly.
bottles of water, bottle of water, bottle of water.
Exactly.
Okay.
So in this case, what we have is each layer will have cell A and cell B.
Okay.
Sometimes many of the batteries or battery modules have multiple more cell type.
Okay.
Depending on the formation or the preparation step that we get before the assembly.
Okay.
So the reason we say this is cell A and cell P, so for the manufacturers will understand that this cell A machine will prep a cell A, will have as many operations as they want to build a cell A.
Okay.
And this will build a cell B.
Okay.
As many operations, as many different operations, it doesn't care really, as long as it can prep cell B.
Okay.
So this is doing cell B, this is doing cell A. What we have then, so these two we call a repeating layer.
Ah, you beat me to it.
Okay, now these two machines is a single layer.
Okay.
Now, the case, which is the case of the module, well, however it looks, it doesn't matter. Different products will have different overhead layers, but in this case station is the overhead layer.
Okay.
So our overhead layer is a single station, and that station is preparing the case and introducing it to the pallet.
Okay.
Okay, so the part comes in, the empty part would come in. So this is an empty part now. It will come in, it will get a case,
Okay.
a pallet. It will get a case, and then it will go and put in the cell A.
Okay.
And then we'll go put in a cell B, and then cell A, and then cell B. Now we have 4 cells out of 8 on that pallet.
So that means
On
we
that
have
case.
to go back around again.
Go back another pass around.
Okay.
And when it goes back another pass around, it will make a complete module.
Okay.
And when it makes that complete module, it will come out of here a complete pallet, like this one, and this unload station will unload it. So now when it turns green, it's unloading. And with this design, it's unloading every 8 seconds, which is basically every other pallet. Now, in this case, we're saying that cell A, cell B, the case, all of these machines, well, these are replicas. So this one is a replica of this one is a replica of this one. But all of these machines have a cycle of the base cycle, what we call a base cycle.
Okay.
And that base cycle is 4 seconds. Okay? Since we're unloading every other one, so every other 4 seconds, that's every 8 seconds.
Okay.
Every 8 seconds. Now you get a module every 8 seconds.
Wow.
The only thing that makes that possible is the math, the process.
No wonder I don't understand.
Okay, so today you cannot do that. We cannot unload 8 cells module in 8 seconds.
Really?
That's not possible.
Okay.
We cannot do it. We have to build multiple systems to be able to get that kind of throughput, because this kind of throughput is at 2 million parts per 2 million modules per year.
Whoa.
This is a huge.
That's a huge jump.
It's a huge. It's very big, and we cannot do it. Okay. Now, if we increase the number of cells in the battery, so some would say I have 16 cells, or I have 32 cells, or I have 400 cells. It does not matter. The machines will be different. The process is always the same.
Okay.
Now, what happens here when we said we're going to scale the system?
Okay.
If we take these 2 machines out, the system runs on a lower capacity.
Right.
Basically, in this case, the system will run on a 16-second cycle time, and that 16-second cycle time is 1 million parts per year.
Okay.
Now, for 1 million parts per year, if we want to scale it to 2 million parts per year, we're adding another layer. So see, we're adding a cell A and a cell B.
Right.
By adding only 2 machines, that's half of the system. We're doubling our production.
Crazy.
2 more machines, triple the production.
And
2 more machines,
you can just keep adding on, and you can extend it, and that you're not extending it another, whatever length this is. You're expanding it
For
just
only
enough.
a double. No, you're only adding 1 layer of machines to be able to get that much, or in this case, 1 million more. 1 million batteries.
And even though this is a smaller prototype, this end here would be able to come off, and you'd be able to extend that, right?
Exactly. That's what we're going to do. So we're going to build the system. These sections are part of the main system that we provide. So we're going to be providing the customers with, or the integrators will be providing the customers with the transport and machines. And what's going to happen is this is a section, and you're free to add a machine to it. And that machine can be manual, semi-auto, or auto station.
Oh.
The process will give you the production.
Okay.
Compared to if you use that same exact machine with the same exact cycle time, the traditional system will give you a much lower production capacity. In this case, if I have a matching system, the production capacity of this system will be 30-second cycle time.
Oh. Okay. That's a big difference from what we have already.
It's a huge difference.
Yeah.
It's a huge difference. And this is where we're going with this. The production capacity increases only because of the math. Only because of the math. Now, what is the cycle time of these? In this case, the cycle time of every machine is 4 seconds.
Okay.
And if you remember when we said there's no bottleneck, which one is the bottleneck? They're all replicas of each other.
Right.
And they all have the same cycle time.
Right.
Now, which one is the bottleneck?
Interesting. Okay,
Gone.
so if
that bottleneck is gone.
the bottleneck is gone, but so when we say, okay, we need to stop a machine, that means you have to take the layer off?
We will turn this machine off,
Then
and the system will take care of itself.
then you can still have this one running.
This is running.
Okay, even with that one out. Okay, because
Yes.
it's gonna skip that, but it'll get it back over here.
Yes.
Right, and then got it. Okay.
Okay. So what's going to happen is we're going to turn this off. Since we have 2 layers system right now, our capacity is 2 million. If we turn any of these 4 machines off, the capacity will go down to 1 million, and the system is still running. It's not stopping.
Right.
Now, that effect, keep in mind the production capacity went down half, 50%.
Right.
That will go smaller, that effect will go smaller than 50% the more layers you're adding.
Okay.
Because every layer effect on the whole system will be a smaller percentage.
Okay.
And that is where we say the more you scale, the more you have overall equipment efficiency. And same thing, if you look at it, this is a constant, and it's on a lower utilization, very low utilization.
Starting and ending, right?
Okay.
They're skipping, and so if
And
I understand this
this-
right, these are being skipped every so often, right? Because it's not.
It will
it's not,
have
it's
to.
not unloading.
Exactly.
Now it is.
So
unloading.
now it's not unloading. When it's a green, it will unload.
Oh, I see.
Yes.
Gotcha. Now it's unloading that one.
Yeah.
It'll start over again, go around in prerequisite time, then get unloaded again.
Exactly. If a customer expressed their willingness to implement this system, what we're going to say is, okay, let's look at the product, define the repeating layer math for you, okay, identify what is the process going to be, and you will have multiple options. One option that we build the whole system for you. We have a fleet of integrators that we partner with, multiple integrators, so whatever you have approved integrator, we can work with them, but we have our own partners that we will utilize to integrate the whole system for you.
Okay.
And they're trained to build machines, and they know how to build machines for the RLP. Otherwise, if you say no, you have your own integrators, that's perfect. What we're going to do for you is we're going to provide you with the transport system and the system controller.
Okay.
And those 2 pieces are enough to assure or to guarantee the process is working the way it is intended.
Okay.
The system controller and that transport system will together have the algorithm and the system that is designed to keep your system running 100% of the time. And the more you have, as I was saying, the more you have repeating layers added, the more you scale your system, the less possibility of any possible catastrophic downtime you will ever experience.
Gotcha.
Like in here, the possibility, the effect of this is only half of the
Right.
production. If you go one more, it'll be 30%. If you go one more, it'll be 25%. If you go one more, and so on.
Right.
And so the step down will be much less if you add more layers.
What happens if, since these are only ran once per
Yes.
per cycle, what happens if one of these go down?
So the system would stop. But
Okay.
how would they go down? And what do they do?
Well, one unloads and one.
That is the point.
Okay.
Now, the efficiency or the utilization of these 2 right now is 50%.
Okay.
So their possibility of going down is half of what these.
Because they're being used more often. All right. So
And
let's
this
say,
is why, and this possibility that you just mentioned is why on the very initial system efficiency, we say it goes to 92%. It's not 100%.
right.
It's 92%. The system, there is an 8% possibility that the system would stop because of one of these 2.
Okay.
But when you add more, at some point, we will add more of these.
Right. Okay. That makes sense.
And now when we have more of these, what happens to the system?
Keeps on running
It's
then.
100%.
Yeah. And then if one of these goes down, it can
Uptime.
continue to run.
It continues
Then
because
can't
it
stop.
already has a backup.
So let's say someone scaled this quite a bit, right? They
Yes.
had huge production, they wanted
Yes.
2 million, but for whatever reason, sales are low, they need to slow down things, for whatever reason. So in that sense, you could have a larger system, but then at the same time pull back on it
Yeah.
and just shut off certain machines and still allow the system to run, right?
Exactly. The
Okay.
system will be running. Half of the system is off. For example, half of the system is off, but the system is producing on lower capacity. you're not running all your machine, you're not consuming all your machines for lower
Right.
capacity.
Right.
Which today, in the traditional method, you have to use all your machines. All your machines have to be running if you're running one part a day or 100,000 parts a day. All
And if
your
you're not
machines
running
to
that
be
machine, then you get the bottleneck, right?
if you're not
Aha.
running that machine, then the system
All right.
stops. Yes,
Yeah.
exactly. In this case, no, you can turn off half of the system.
And then if things start getting better again, or for whatever reason, you can turn them right back on again and
Yes.
keep things moving even faster and
Yes.
get more production out of it.
And then there was, so every time we introduce this system to somebody else, and we've introduced it to quite a bit of people from universities, from experts in the industries, and every time we introduce it, they come to us with new benefits. And one of the people said, what if, hypothetically, we add an unused layer of machines? And this unused layer of machines will kick on when any of the layers turned off.
Right.
So now your uptime is 100%. No question asked.
So if the machine goes down, you have that one backup.
That one backup is already
Copy
ready
that.
to go. It will go right away. We're done.
Okay.
Okay? Now, what is the other advantage of having that left in? If a customer comes in and said, well, I want more of this product, and you want to increase capacity.
Turn it on, and now
Okay?
they all run.
When do you want it?
Right.
When
Okay.
can you do it? Right? Well, right now.
Right.
Turn them
Turn it
on.
on. Bingo,
Turn them
bango.
on, and this is where zero time to market means.
Interesting.
Now, if we're saying zero time to market, this is a big deal. If I want 100,000 more parts from you, and you can click a button and start producing 100,000 more, this is unheard of.
Right. Okay. So let's take a step back, and we talked earlier about how our nation is falling behind as far as the battery
Yes.
production, right? Obviously, overseas you have rampant production of EV batteries. Tell me more about how this is going to just destroy that idea.
So here's what we did. We took a sample of an incremental investment to build battery systems with a traditional method,
Okay.
and an incremental investment for this method, for
Okay.
the RLP. And we said that over 5 years, how many products we will produce with the traditional method at the end of 5 years will actually produce, and how many we will actually produce with the RLP.
Okay.
And we found out that with the traditional method, we will be producing 3 million and something batteries.
And right now our capacity is what?
Okay. Well, this study does not consider the capacity.
Okay.
This study considers the accumulated production.
Okay.
Okay. Over 5 years, we're building 3 million. We go to the RLP. We run the exact same investment plan, and we see the RLP going to 8 million
Whoa.
over 5 years.
Okay. That's a big jump.
That's a huge difference. Now the final production capacity, the throughput over the annual throughput, is more than double on the RLP side. But keep in mind, we're using the exact investment plan. We're investing the same amount of money.
Wow.
If not a little less, the RLP is producing a lot more,
Right.
which is crazy.
Right. So in that sense, that will allow us to catch up with the rest of the world, right?
So if we can use our current investment plan or current investment rate, we can catch up to the other side of the world in about 6 to 10 years.
Wow.
We will pass them over.
Okay.
Yeah, that's how fast we can go in with the current investment rate. But why do we go with the current investment rate?
I don't know. Because that's what we're doing now?
If we go double,
Uh-huh.
if we go double, that's what is expected. If we go double, you're talking about 3 years.
Oh, okay. Okay.
You see where it's going?
Yeah.
With a little bit help of the government, with a little bit of help with the investors to go in to raise the capacity or the throughput of production for the US, we can do it in under 5 years.
Wow.
We can pass any production capacity possible outside the US and even start exporting because we don't need all that. We can cover the whole world with it.
Wow.
With the production out of US.
Okay.
Yeah.
That's
and
crazy.
Since we're here in Michigan, we're planning that our center of excellence will be here in Michigan, and we will be doing a lot of projects here in Michigan. Most of the projects that we will be handling, because one of our one of our business models that we do is we would handle the production.
Okay.
The complete thing, investment, everything. We build the manufacturing capability, and the customer will get their batteries.
Wow.
Okay. Now, with that, we're planning to do all of that in Michigan.
Michigan.
So Detroit
Good to hear.
is once again the center of the manufacturing or the industrial boom for the world.
should be.
Yes.
That's right.
That's what we're living today.
Well, there you have it, folks. RLP, the future of assembly. Come check us out at the Battery Show in Detroit this October. See you then. Thanks, MJ.
Thank you very much.